Okay, today we're going to apply what we've learned about atoms and molar masses and Avogadro's number, and then put them all together. We can convert between grams, moles, and atoms by using molar mass and/or Avogadro's number. So this flow chart, I would very much encourage you to write down, okay, and write it on its own little piece of paper. You can kind of keep it as a cheat sheet for right now. Okay, so there's three options we can have: grams, moles, or atoms. Okay, and atoms the same thing as a particle. Those things are used interchangeably. So if I'm going to go from grams to atoms, so this is just a conversion. That's why I taught conversion the way I did. I'm going to go from grams to atoms, or probably grams to moles. I can do that because I know the molar mass is defined as the number of grams per 1 mole. So by using that, if I'm going from grams to moles, I would multiply by 1 mole over the molar mass. If I want to go the other way from a mole to a gram, I would do the opposite thing. I would put the molar mass over 1 mole because the molar mass would be grams per 1 mole, so be left with uh, grams there. I can go from moles to atoms. I have the conversion factor between there. It's Avogadro's number. Okay, so in 1 mole, there are 6.022 times 10 to the 23 atoms. So if I want to go from atoms to moles, I would do the opposite way. 1 mole over 6.22 times 10 to the 23 atoms. I can go from grams to moles very easily. That's 1 mole over molar mass. I can also go grams to atoms. That would be a two-step conversion problem. I have to go through moles first, and then I multiply by one Avogadro's number over 1 mole. I can work it backwards. I can go from atoms to grams, multiply by 1 mole over Avogadro's number, then times molar mass over 1 mole. Notice in that case, my moles would cancel. My atoms would cancel because that's what my unit on the top is. So now let's work some examples of this. This is really our first introduction into stoichiometry. So my first example is going to say, how many atoms are there in 3.25 moles of NaOH? So in any, oh, that's way too big. And that even bigger. So when I'm doing these things, this is a conversion problem. I want to take what I know. I know I have 3.25 moles NaOH. Now looking back at my flow chart, I am in moles, and I want to go to atoms. So I'm going to use the Avogadro's number. I'm putting that over 1. So times mole NaOH goes on the bottom because that's what's on the top of step 1. And on the top, I have a direct conversion factor. I can tell you that almost anytime you're using a conversion, and this is most of the time true, it'd be 100% true for this unit, you always put a 1 in front of there because molar mass is defined as the number of grams per mole. Avogadro's number is the number of atoms per 1 mole. So an Avogadro's number would be what goes on top, 6.022 times 10 to the 23 atoms NaOH. Moles NaOH cancel. Moles NaOH cancel. So now what I'm left with is 3.25 times 6.022 times 23. Pull out my handy dandy calculator. Clear that calculator out. Pull out my handy dandy calculator, and I would do that. 3.25 times, I like to put parentheses around this because order of operations every now and then gets you 6.022. Let me think how to do it on this. Oh, here we go. Oh, I'm sorry, I hit the wrong thing. We go to your decimals calculator that you guys use. Let's try with that one. Same thing, but I would want to go to. I don't like decimals. Is this what y'all decimals look like? Let's go to a graphing calculator. Let's see what this one looks like. So I would type in 3.25 times 6. Maybe not. Times 6.022 times 10 to the 23rd. Oops. 10 to the. Gosh, let's not use this decimals. Let's just go back over to the calculator. I apologize for this little inconvenience here. So I'm trying to find, I keep hitting the wrong button. Let's go to this calculator. We can go to a scientific calculator. I like this one a little bit better. I like this one. So let's say 3.25 times, I like to put my parentheses around my 6.022. 6.022 times 10. Hold up. Okay. Okay, so let's work this one out again. Okay, so it was 3.25 times parentheses 6.022 times 10 to the 23rd. Close parentheses, close parentheses. And that answer equals, it is right up here. It's this number. I need to probably put this in scientific notation. Now, the rule here is how many significant figures. I started with 3, so I probably should have 3 in the answer, okay, because 6.022 has 4, so my fewest number there is 3, so I need to round this to 3 significant figures, so it would be 196 times 10 to the 3, 6, 9, 12, 15, 18, 21, 22, 23, 24. So 1.96 times 10 to the 24th. Let me share my other screen. New share. That equaled 1.96 times 10 to the 24 atoms. Our labels are very important in a OH. So now let's do another example. File new. My second example tells me, it asks, how many grams are there in 3.25 moles of NaOH? So once again, I'm using my flow chart. And I'm going from moles, because that's what they gave me, to grams. So I'm going to multiply by the molar mass over 1 mole. Multiply by the molar mass over 1 mole. So let me find my old pane again. So my first step in any conversion problem is to take what I know, put it over 1. So I know I have 3.25 mole NaOH over 1 times a fraction, the unit on the top, mole NaOH, on the bottom, and we always put a 1 in front of there. And now I need to calculate my molar mass. So my molar mass of this is going to be equal to 22.9898 times 1 plus 15.9994 times 1 plus 1.00795 times 1. Now, I need to, my rule here is most of it, I'm multiplying things by 1, so I don't have to worry about that. So my fewest number of decimals here is 4. My highest number is 5. But I'm going to need to have the same number as my fewest number of decimals. So I put that in my handy dandy calculator. And I get this number. I get the molar mass is equal to 33.99715. However, I only need 4 decimals, so my fourth decimal is 1. The number after that is exactly 5, so I'll round to the even number. So my molar mass sorry, that was 39, my dyslexia, 39.9972 grams NaOH. To solve this out, I would do 3.25 times 39.9972. Started with 3 significant figures. My calculator answer I get is my calculator answer gets 129.9909. I need to turn that to 3 significant figures. So I would say that would be 130 with a decimal point grams NaOH. That was going from grams to moles. Another example. My next example. In moles are there in 75.0 grams of H2O. So I'm going to go from grams, mass, to moles. I'm going from mass to moles. So I'm going from grams to moles. So I'll multiply by 1 mole over the molar mass. So first step in conversion problems, take what I know, 75.0 grams H2O over 1 times grams H2O goes on the bottom. I want to go to moles, and so I'm going to use the molar mass. I know the molar mass is defined as the number of grams per 1 mole. I know already, you have to go calculate it, that the molar mass of H2O is 18.0153. So now to solve this out, I would grams H2O cancel. I would do 75 divided by 18.0153. And that equals 4.63. I need 3 significant figures, so 4.16 moles H2O. Let's do another example. Next example says, how many moles are there in 6.25 grams of acetic acid? So I'm starting with atoms, and I want to go to moles. So I'm going to multiply by 1 mole over the Avogadro's number. So take what I know, put it over 1, 6.25 times 10 to the 24th atoms. I need to put I can't just put acetic acid. I have to put my formula there, which is HCH3CO2 over 1 times atoms. Acetic acid goes on the bottom. One mole, one always goes in front of mole in a conversion factor. 1 mole HCH3COO. And I don't need to find my molar mass because I'm looking for atoms. When I'm using atoms, what always goes in front of atoms is Avogadro's number, 6.022 times 10 to the 23rd. So in this case, my answer is going to be in mole acetic acid because atoms cancel out. And to solve this out, I would divide this one. So it would be 6.25 times 10 to the 24th divided by 6.022 times 10 to the 23rd. And I get 10.3786, okay? I need to round up to 3 significant figures. So it would be 10.4 moles HCH3COO. Okay, so those are the one-steppers, okay? Because those are going from either atoms to moles, moles to atoms, or grams to moles, or grams to atoms. So now our next thing is we're going to take 2 steps in these. Okay, we're going to take 2 steps in these. So new example. How many grams are in 6.025 times 10 to the 24 atoms of carbon? So back to our thing, I am in atoms. I want to go to grams, but I can't go directly to grams. I have to go through moles first. So I'm going to multiply, take what I know, multiply by 1 mole over Avogadro's number, then multiply it by the molar mass over 1 mole. So first thing I need to do is take what I know, 6.25 times 10 to the 24 atoms C, put it over 1, times atom C goes on the bottom. 1 mole, remember, I'm still in carbon, and our middle box is moles, and we always put a 1 in front of it. The Avogadro's number goes in front of atoms, so 6.022 times 10 to the 23 times mole C on the top, 1 mole C, and I know that the molar mass of C goes on top, so gram C, and that's 12.0108. Now to solve this out, I would do 6.25 times 10 to the 24th times 12.0108 divided by 6.022 times 10 to the 23. So when I do that, when I do this, I get 124.655. I need 3 significant figures. 6.25 has 3, 6.022 has 4, 12.0108 has 6. So my fewest number there is 3. So my answer would be 125 grams C. Right, last example. So let's say this one, we're probably going to go the other way. So it's going to be our 2-stepper. Still going to be a 2-step problem. And the question is, how many atoms are there in 1.00 grams of hydrogen? So take what I know, 1.00 grams. This is H2, hydrogen, a diatomic element, over 1, times grams H2 goes on the bottom, 1 mole, H2 goes on the top. And I know this value that goes in front of grams is the molar mass. In this case, it's 12.0 or 2.01590. Grams cancel, times, we're in moles right now, we want to get to atoms. So 1 mole, H2 goes on the bottom. This H2 is on the top here, we always put a 1 in front of mole. And then on the top would be Avogadro's number, 6.022 times 10 to the 23, so 3 atoms. H2, make sure you're putting your unit tags on there. That will really make a difference later on in the semester. So solve this out. Don't really need the 1.00, but so it'd be 6.022 times 10 to the 23 divided by 2.01590. And I get a really, really, really big number. I'll share this screen, that way we can look at it. I get this number right here, 298.7 whatever. I need 3 significant figures, so that would be 299 times 10 to the, start counting decimals, 3, 6, 9, 12, 15, 18, 21, 22, 23. So this answer would be 2.99 times 10 to the 23. 2.99 times 10 to the 23 atoms H2. Remember, atoms, particles, and molecules are all the same thing. So if you do your homework today, you also had that polyatomic quizzes that will take the place of your naming quiz this week. Let me know if you have any questions. Thank you.